We talked about normal distribution last week. If you remember, normal distribution has two types. One of them is called standard normal distribution or standard Gaussian distribution, whose mean is zero, and standard deviation and variance is 1. Okay, so the mean is 0, this is the mean, and this variance is 1. Okay, that's the standard normal distribution. So the area under this curve is 1. Half of this one is 1/2 is here, 1/2 is here. Okay, so this part is 1/2, this part is 1/2. So half of the figure, or half of the curve is 1/2, the other half is 1/2. So it's a symmetric probability density function. Okay, this is a PDF for normal distribution. We will see this a lot in our course. And then if you want to change from 0 mean and 1 variance or 1 standard deviation, you can do that if you multiply your random variable with respect to z by sigma. Okay, any sigma is something that you want to adjust your standard deviation for. Okay, this is something that you're going to adjust. And then this is the mean that you want. Okay, so you want something like that, and the mu will be here and standard deviation will be here. For example, mu will be 10, standard deviation will be 2. Okay, then this normally, like standard normal distribution is 0 mean, 1 standard deviation. Now it is 10 mean and 2 standard deviation. Okay, so I can change how my normal distribution is distributed. Okay, so finally I will have a generalized, okay, this is called generalized random normal distribution. Okay, it has a mu value and it has a standard deviation or variance value. This is the variance, okay, sigma squared, and sigma is standard deviation and mu is the mean. So I will have such kind of distributions. Okay, for example, the mean is 2 here and the standard deviation is 1. If I increase the standard deviation, you see the distribution becomes much wider. Okay, I can shift the mu to -2 and then see that the sigma 1 means sharper distribution, sigma 2 means wider distribution. Okay, so I hope you get the main idea. We did one example of IQ last week. Okay, IQ, the probability of someone having an IQ below 90. Okay, so I'm gonna explain this in the coming slides, so I don't want to spend time right now because we did that last week. And then we will also be able to find the probability of any randomly selected person having an IQ above 140. You see it is very, very low. So now one critical thing was this thing, z is equal to x minus mean divided by standard deviation. So what is the thing that we are going to do? Here is the example. Okay, I'm starting to discuss new things right now from now on, but they are related to what we covered last week, guys. Okay, so I have a college entrance exam, normally distributed, scores are normally distributed with the mean 82 and standard deviation 8. So I have this distribution, okay, bell curve, mean is 82, mu is 82, and the standard deviation is 8. Now, this is the PDF of like this, 82, 64, okay? You say that my distribution X is normally distributed, whose mean is 82 and whose sigma squared is 64, okay? So standard deviation is 8 and variance is 64. So what is the next step? I need to change this into a zero mean and 1 standard deviation distribution type. Okay, I want to standardize. Okay, I want to standardize my distribution. Okay, from an 82 mean to 0 mean, and from 8 sigma to 1 sigma. How do I do that? If I subtract the mean, okay, x minus mu divided by the sigma or standard deviation, I will have a new variable, okay, new random variable, which is z. Okay, now it is normalized and standardized. Okay, now I have my x random variable, okay, and it is now z. Okay, x is from this one, this is x, and this is z. So what is the thing that I need to do in such questions? Because what is being asked in the question, what percentage of the students score less than 84 on the exam? Okay, so what is the question? I want you to tell me, okay, let us change the color. Okay, I want to find out the probability of people having a score less than 84. Okay, here is my x-axis. So I want you to find out the area here. Okay, so 84 and below, less than 84. So how do I approach to this problem? I will say my x is 84 and my mu is 82. Divide by 8. Now I will have my z value. Okay, what is the z value? 2 over 8, which is 0.25. Okay, so this is the first step of my solution. Okay, I hope you understand what's going on. I have a distribution of this normal distribution with 82 mean and 8 standard deviation. Now I'm trying to convert it to a standardized z distribution. How do I do that? I'm going to get my 84 minus 82, which is the mean, okay, divided by the standard deviation. Now I will have z equals 0.25. Okay, now I should come to the z table. Okay, this is the z table. How do I read the z table? My z is 0.25. Okay, I'm going to come here, find 0.2 here. It says 0.25. So 0.2, 21, 0.22, 0.23, 0.24, and 0.25. So this is what I need. Okay, it's a table which does the calculation automatically. Okay, I don't need to do any integrations or anything. Now I can say the probability of obtaining a student who has a grade less than 84, okay, who has a grade probability of a person, randomly selected person, whose grade is less than 84, is now probability of z being less than 0.25, okay? So this z table will give me this point 0.5987. What does it mean? It says around 60% of the students score less than 84 on this exam. Okay, so the middle part is 50%. So it's a little bit over 50%. So totally it is 59.87% of the students will get a score less than 84. That means if I randomly select a person who takes this exam will get a score less than 84, is the probability this one, okay, 0.59. That means 59% of the cases I will select a person who will get a score less than 84. Okay, is that clear, guys? Did you understand this part? I think this is the most important slide of today, okay, one of the most important slides, because I try to give you a sense of how should I go from such a question into the Z table, okay, this is Z table, and you're going to do the same thing in the final exam, in the quizzes that is coming, okay? So please try to understand this part. I have a general distribution. I convert it to a standardized distribution or standard normal distribution, then find the Z value. Okay, so this will be my Z value, which is 0.25, mean is 0. Now I'm interested in the area here, okay? Not this one, but this one, okay? I'm interested in this one. So I'm interested in this area, okay? So Z is 0.25. Then how can I find this area? I need to use Z table. Then I go down, okay? Find 0.25, 0.2, 0.25 is this column, okay? If it were 0.27, what would it be? This one would be 0.27, 0.29, okay? 0.30, 0.51, for example, okay? This is 0.51, this is 0.30, this is 0.25, 0.27, 0.29, okay? This is 0.29. So you're going to learn how to use Z table today, inshallah, okay? So now it's your turn, guys. I'm going to give you one example, okay? So here's the example. The height of plants in a certain garden are normally distributed with a mean of mu 26.5 inches and a standard deviation of 2.5 inches, okay? I am plotting the normal distribution whose mean is 26.5 and sigma is 2.5, okay? Sigma is 2.5. Now, approximately what percentage of plants are greater than 26 inches tall? What does it ask? Okay, give me, okay, let me go to the green, red again. Now, I need this, and I want you to find out the area here, okay? Greater than 26 inches tall. So, what is the probability of obtaining a plant whose height is greater than 26 inches, okay? Or what is the percentage of plants whose heights are greater than 26 inches tall, okay? Now, I want you to solve and write in the chat and then tell me what the Z value is, okay? Just Z value, please. Okay, I forgot to start the recording. Did everybody understand what's going on here? So I have this thing. The mean is 26.5. The standard deviation is 2.5, and I will standardize this distribution by converting everything to Z. Z is like 26 minus 26.5, which is the mean. 26 is given here. So what is being asked? Probability of X greater than 26. Okay. So I should convert this into probability of Z greater than something. How do I find this value? Using this Z equals X minus mu divided by sigma, which we found as being minus 0.2. So this will be 0.2. So now it should be this area. Now we found minus 0.2. So using the Z table, we found that 0.4207 is the area which is less than minus 0.2. So we are interested in this area, which is probability of Z greater than minus 0.2. So that's why I say 1 minus this area, 1 minus this area will be this area. So 1 minus probability of Z being less than minus 0.2, which is 59% almost. Okay. Now it's your time again. Now I want you to give me the final result. Okay, use the Z table on the net and give me the probability. What is the question, guys? The weight of a certain species of dolphin is normally distributed with a mean of 400 pounds, okay, almost 200 kilos. So this is 200 pounds, 400 pounds, and the standard deviation is 25. How do we get these numbers? From the scientists, okay? They measure the weight and the weight of certain dolphins, and now I want you to find out the weight, the percentage of dolphins whose weight is between 410 and 425. Okay, this area. Probability of the weight of a dolphin is between 410 and 425. Okay, this is what is being asked. Now I want you to find out. Tell me what is the percentage. Okay, tell me this. Okay, in terms of percentage or probability. Okay, it's your time now. Reminding me. Okay, so I have a distribution like this. 400 is my mu, and I want you to find out this area, which is the probability of obtaining a dolphin greater than having a weight of greater than 410 and 425. So this is my probability. And now I'm going to convert everything into Z, okay? Probability of Z1 greater than Z1 and less than Z2. So now I'm going to first find out the Z1. So this one, okay, I'm going to convert this into Z1 and convert this into Z2. Then I'm going to have such a distribution, guys, okay? Now this is 0, and this is going to be Z1, and this is going to be Z2. I'm going to find out the area using these Z1 and Z2s, okay? And divide by 25, which is 10 over 25, which is 0.40, okay? And what is Z2? 425 minus 400 divided by 25, which is going to be 1. So what is this? What are the Z table values? Okay, here it says 0. Probability of Z less than 0.40 is 0.6554. Okay. Then I go here. I looked at this one, guys. 0.4, and this one is 1. Okay. What is it? 8413. So probability of Z being less than 1 is equal to 0.8413. So what does this mean? This is probability of obtaining less than 0.4 is this one, and probability of obtaining less than 0.1 is this one. So if I take the subtraction of these two, probability of Z less than 1 minus probability of Z less than 0.4 is going to be the result, okay? 0.8413 minus 0.6554, which is going to be something like 19%, okay? Very close to 19%. Is this clear, guys? Did I make everything clear here? Do you have any questions at this point? So what is the question? I want you to find out the percentage of dolphins with this weight interval, okay? 410 and 425 pounds. So how do I do it? I want to find out this area, okay? The whole area is 1. Half of the area is 0.5. So I'm interested in this. How do I do that? I convert everything, this X, these values into Z values. I found 0.40 and 1 as my Z values, okay? Now it is between 0.40 and 1.0, okay? How can I find the probability here like this one? Let me once again tell you, if probability of z less than 0.4 is given as, let's say, 0.65. What does it mean? It's going to be like this, okay? This is 0.4, and the area under the curve less than 0.4 is 65, okay? So this is half, 0 mean, and more than half, it should be 0.65. If I say probability of z less than 1, it is going to be something like that, okay? And it is going to be even larger, which is like 85%, right? 84%. So this is 0.84 is my area. So how can I find the area between 1 and 0.4? It's going to be something like that. So probability of this minus probability of z less than 0.4 will give me probability of z between these two values. Okay, is that clear enough, guys? While finding, hocam, will we not write z greater than z1 while finding the probability? I mean, yes. For example, what I understand from your question, Emirhan. For example, if I have, let me find a spot to answer your question. For example, I have this distribution, and it is asked like 0.4 is here, and it's being asked like z greater than 0.4. How can I find that? Okay, it is given 0.65. How can I find this one? 1 minus 0.65. Okay, like 0.35 is going to be the answer. Okay, so this part is given in the z table. So which is 0.65, and it is being asked to find this part. Okay, so how can I find it? The whole area under the curve is 1. 1 minus 0.65 will give me the area here. Okay, the area here. This area is asked because probability of z greater than 0.4 is this one. So I need to subtract 1 from this. 1 minus 0.65 is going to be the probability. Okay, is this clear, Emirhan?
Yes, hocam, thank you.
Okay, thank you very much for asking. Let's go to another example. Now I want you to read the question and do the calculations and send me the result through chat, please. Arkadaşlar, if you can do these calculations, the other things are all just checking the z table correctly, okay? How do I do that? 778. So I'm going to convert this into a z distribution like this, right? So this is going to be 0, this is going to be z1, this is going to be z2, okay? So how do I calculate z1? 778 minus 800. So don't be confused. You have to put x first, okay? Even though x is small, you have to find a negative number because it is on this negative side, right? This is on the negative side of the things, okay? This is negative. This is the positive side. So this is like minus 22 over 40. And if you come here and 34 minus 800, this distance divided by 40, which is like 34 divided by 40. Can you tell me the numbers here, guys? Can you tell me the numbers? Minus 22 minus 40, what is it? Minus 22 divided by 40, what is the number?
0.55, hocam.
0.55, which is minus 0.55. What is this one? 0.85, I guess, right?
Yes.
Yes. So now my distribution is between minus 0.55 and 0.85. Okay. So here is the area. So I'm going to go and find out probability of z less than 0.85. And I'm going to find out the probability of z less than minus 0.55. And then subtract these and find my result. Okay. The other things are just checking the table, okay? I'm going to go and find out the table, okay? This is I think I put the wrong, no, I'm going to use this table, minus 0.55. So here, 55. So I come here and find out 80. So here is, I'm gonna tell you how I use this table to find out minus 55, okay? So in this table, I see plus 55 being almost 71, okay? Plus 55, so 0.55. So it's been given that this is 0.7088. How can I find minus 0.55? This is going to be 1 minus 0.8788 is going to be the probability of Z less than 0.55, okay? The whole thing, this table gives me this area because my distribution is symmetric, okay? It's going to be this area will be the same thing with this area, okay? The area below minus 55 will be equal to the area above 0.55. So the table gives me the area here, okay? The area here. So this one is given. I want this area, okay? I want this area. So this whole thing is given, this green thing is given as 0.7088. So how can I find the green one? I can find it as 1 minus 0.788. Okay, then this is what? Probability of Z less than minus 55. Okay, so this is critical that you understand this, how to read the Z table that I give you. Okay, in the exam, I'm going to give you the Z table, and you're going to do the calculations accordingly. Okay, so one of them is what is the first one? 80%. Okay, which is probability of Z being less than 0.85, and this one is 29%, and the remaining is 51%. Okay, the probability of having this is 0.51, and obtaining a light bulb, which is in this life, let's say duration, is going to be like 51%. Okay, did everyone understand what is going on in this part, arkadaşlar? This is the end of the probability calculations using the Z table and the problems. Okay, any questions so far that you didn't understand this part? Okay, I'm gonna give a break in a couple of minutes. Okay, maybe 5 minutes. So let's continue at this point. So we are starting to discuss some terms about statistics from now on. Okay, very, very important. We talked about representative sampling from the population. Okay, let me talk about these topics first. Okay, guys, I have this population. Okay, let us, for example, Kayseri people in Kayseri, and then I'm talking about their age distribution. Okay, what is the mean age of Kayseri people living in Kayseri? Okay, or AGÜ students GPA. Okay, all AGÜ students GPA. This is my population. Okay, and I'm interested in the GPA of mean GPA of this AGÜ students, or mean age of people living in Kayseri. Okay, I will not be able to go and ask each and every person in the population. Okay, I don't know. Like there are 1.5 million people in Kayseri, and I cannot go and ask each and every person. That's why I take a sample. Okay, now it's going to be my data. I'm going to ask, let's say 1,000 people, what is their age? But when I'm asking this sample, when I'm choosing this sample, it should be very important to choose which people to ask. Okay, for example, it should be representative. Okay, there should be people from child and many other things, or I'm interested in the mean monthly income of people living in, let's say, in one neighborhood. Okay, I'm interested in, this is Kayseri, I'm interested in one neighborhood, and I want to find out the mean income, okay, monthly income. So it's not very easy to find out, and I'm going to go and ask, let's say 1,000 people or 100 people. Okay, but I need to choose such a sample that it will be representative of all, let's say, all backgrounds, all age groups, and so on. So this will be a representative sample. Okay, representative. There is another term called stratified random sampling. Okay, for example, there are a certain number of students at AGÜ. Now it is 3,000. Okay, maybe 4,000, and only 30% of them are female students. And what should I do in order to select 50 students? I should do like 15 of them should be female and 35 of them should be male students, in order to do some calculations related to the gender. Okay, so these are critical things. I have to have representative samples. I have to have, I can do some stratified random sampling. That means there are two categories, category 1 and category 2. And in the population, this category is 30%. This category is 70%, okay, in the population. Okay, in the sample, it should be the same thing. Okay, sample category 1, again, the population is 1.5 million or 4,000 people at AGÜ. Now I have 100 people in my sample, and in out of 100 people, category 1 should include 30 students. Category 2 should include 70 students. Okay, so this is called stratified random sampling. This is something that we do in machine learning or in artificial intelligence problems. Okay, so here's the critical thing. I say population is all possible values. Okay, all people's incomes in that neighborhood, in that city. Sample is a portion of the population. I cannot go and ask every cancer patient. I cannot go and ask all military personnel, but I can take a sample, and then I will try to do some inference, çıkarım. Okay, I'm going to try to find out what's the mean GPA of AGÜ students, what's the mean income of the people living in this neighborhood, what's the mean or variance of this value, okay, kind of things. Okay, the parameter is going to be something related to the population. Okay, population mean, for example, population mean is a parameter. Okay, parameter. But from the data, I will have a statistic. Okay, which is going to be the sample mean, for example, sample mean. You know, sample mean can be different from the population mean, right? Değil mi arkadaşlar? I may have 1.5 million people in Kayseri, and I'm choosing 1,000 people, and the sample mean can be totally different from the population mean, or it can be close to the population mean. So statistic, it's not statistics. Statistics is the science of this topic. Now it is statistic. I obtained statistic from the data in the sample. Okay, I collected data from a certain population. Okay, I have this population, and I chose this sample. The population mean is mu. Okay, mean. and the sample mean is x hat. Okay, sample mean. I have there are 1.5 million people here. I have only 1,000 people. Is this clear, guys? Do you understand the difference between parameter and statistic? Is that clear? I want to see some thumbs up or okay kind of thing in the chat. Please do so. Everything is clear, right? It's very easy. I want you to understand this topic right now. Okay, so it is something that you should bear in mind, that we have two topics: population mean, which is something that we want to find out. Okay, we want to estimate. How can I estimate the mean income? I can take a sample, do the calculations on the sample. And what is the main goal? I am trying to find out an inference, çıkarımda bulunmak. I want to find out something about the mean. Okay, we will do some calculations according to that. Okay, so it is 9:40, and after the break, we will go into a very important topic called central limit theorem. I will start with a MATLAB implementation on my laptop, and then on MATLAB, and then we will continue with that. Okay, so let's have a 10-minute break. We will meet at 9:50, inshallah. Okay. So here is one example for you. Okay, I have a random number generator whose type is uniform random number generator, and I will generate a number between 1 and 100. Okay, and it will be 100,000 numbers. Okay, it will try to simulate the people's ages. Okay, age. Like there are people with age 1, and there are people with age 100. Let's say the distribution is uniform. Okay, I'm evaluating this distribution. That means I have many people here, 0 age up to 100 age. Okay, so what is the mean? The mean is around 50. Okay, I found the mean as 50.55, 58. And then now I'm going to do something. I'm going to take samples from that 100,000 people. Okay, I have 100,000 people in my population. I'm going to get only 100 people from this population. This is my sample size. Okay, 100 is my sample size. That means I'm asking to 100 people. Okay, then I take their ages. I go and randomly pick 100 people, ask their ages, and then obtain a sample. Sample is here 100 numbers. You see 100 numbers. Okay, with different ages. Okay, 88.4, 37.2, and so on. There are many age numbers here. So then I take the mean of that sample. Okay, out of 100,000 people, I choose 100 people, and I take the sample of that age group. Okay, of that 100 people. This is going to be what? Sample mean, right? Sample mean. This is the population mean. I have 100,000 people, and I found the population mean, and it is uniformly distributed. Every age has the same probability of obtaining, right? This is what it is. Almost the same probability for a person who has 50 years old age or 10 years old age. Okay, which is not the case in regular population, but I want to show you something here. Okay, so then I do this sampling. I do the sampling 1,000 times. Okay, 1,000 times sampling. from 100,000 people, I choose 100 people. I do that 1,000 times. And each time I record the mean of that sample. The sample means are recorded, okay, in this mean of sample vector. Then I will plot it and then find the mean of the means. Okay, let us find the mean of the means. Let's see what it is. Okay, I'm gonna evaluate this, and here is the uniform distribution from 100,000 people, and here is the mean distribution. Okay, sample mean distribution. You see, it is kind of a curve shape. Okay, bell curve shape. Çan eğrisi gibi, right? Normal distribution kind of. Okay, and then if you check the mean of the means, it is 50, right? 50.52. What was the original population mean? 50.58. What did I find by running many times? I went and asked 100 people, what is your age? What is your age? What is your age? I recorded them, but I did that 1,000 times. And then I plotted the histogram of the means of these 100 people sample, and then I saw that the distribution is normal distribution, and the mean of those means is highly similar to what the population mean is. Okay, this is called sample mean distribution. Okay, this whole graph is called, histogram is called sample mean distribution. Sample mean distribution's mean is gonna be the mean of the population. Okay, that's what central limit theorem says. If I take many samples from the population, and if I take the mean of those samples, the mean of those means will be equal or very similar or very close to what the population mean is. Okay, I don't know the population mean of Kayseri people's ages, let's say. What I'm trying to find out is by sampling from that 100 people, and then by that sampling, I will try to estimate what is the actual population mean. Okay, so for example, if I wanna change the size of my sample from 100 to 1,000, okay, now I'm gonna go and ask 1,000 people, ask their ages, and see how this graph changes. You see, it is a much better Gaussian shape. Okay, if I ask more people, if I have more data to estimate the sample mean, then I will have a better Gaussian distribution. Okay, and the mean is still 50.60, right? What was the original thing? 50.58. Now I found 50.60, right? I don't know the actual mean. I'm just sampling, and many sampling. From those samples, I find the means and plot the means and find out what is the mean of those means, and it will give me the population mean, right? It's very handy. It's very nice thing. Okay, we will use that very often in our case. If I don't ask 1,000 people but ask only 10 people, what will happen? Let's see. Now I'm gonna say, even by asking 10 people, okay, it's gonna be like Gaussian shape, but now the standard deviation has changed. Okay, let me plot this for 1,000 people and put it side by side. Now I change my sample size from 10 to 1,000. Okay, this is 10 to 1,000. This is 1,000 people situation. This is 10 people situation. Okay, do you see the difference, guys? Here is the values are changing between 48 to 53. here the values are changing between 20, 25 to 80, right? That means standard deviation or the variance is high for fewer number of, if the sample size is low, okay? Sample size here is 10, sample size here is 1,000. So I ask 1,000 people, get their means and plot this, repeat this 1,000 times and see that the distribution is Gaussian and the mean is much more similar to what we have in the population. On top of that, I will have the standard deviation is smaller, so it is good to have such a standard deviation small case. But here the standard deviation is large. That means my mean value will, even though the actual mean of the population is 50.58, I will find out in some cases, according to the selection that I do, I will find some cases like 20 or 80, right? So because I will go and ask only some old people and find out the average being 80. I will go and find very teenagers and find out teenagers and young people, then I will find out mean age as being 25. But if I go and ask 1,000 people, I will have a better distribution. I will have a better understanding or estimation of what the actual mean is. So that's why the standard deviation of this distribution will be smaller, okay? What's the take-home message? If my sample size increases from 10 to 1,000, my standard deviation or the variance of my distribution of the sample means will be much sharper, okay? It is much sharper. It's going to be much wider, variance is higher if my sample size is low, okay? 10 people, 1,000 people, okay? So that's what I would like to tell you about central limit theorem. One more thing, which is also critical. Now, I don't want to do any age, but this time I want to do photon count, which is related to exponential distribution. Okay, let's say something like exponential distribution or Poisson distribution. Okay, so now I'm gonna generate again 100,000 numbers according to the exponential distribution. Let's see what is the what kind of a distribution it is. You see, this is an exponential distribution. Mean is 10. Expected value is 10. I adjusted it here. Now I'm gonna go and find everything for photon count. Okay, and then let's see how my thing works. You see, I have 1,000 samples, photon count, let's say, or the amount of time that I'm waiting for something. Okay, it will be small. As I go further, it will be larger. Exponential distribution, the probability of obtaining something as x increases will be lower. That's the thing about exponential distribution. So I found this is my distribution of the means, and the mean has been found to be 10.01. Actual mean was 10. This is what I told this to become. Okay. So what is the central limit theorem also says? Irrespective of what my distribution is, it is exponential distribution, uniform distribution, normal distribution, chi-square distribution, a gamma distribution, anything like that, I will be able to take samples from that population. I don't know what the distribution is. I will take many samples. Okay, take one sample, do it again, do it again, do it again. If I repeat it many times, I can find out the mean of that population. Okay, that's the main idea behind all this topic. Okay, now I want to stop sharing the screen. Now I want you to write, what did you understand? And this is a quiz right now. I want you to understand I want you to write me on chat, what did you understand about central limit theorem according to what I explained to you? Okay, you can read from the web, but write in your own words. You have 1 minute to write something about central limit theorem, what it says. Okay, this is a quiz for today. Okay, I'm expecting your answers in the. Okay, we talked about central limit theorem on MATLAB a couple of minutes ago. So what is the central limit theorem? Is if we are sampling from a population with unknown distribution, okay, unknown distribution, irrespective of the distribution, like normal distribution, uniform distribution, chi-square distribution. So I don't care which distribution it has. The sampling distribution of X bar, okay, this is called sample mean. Sample mean. And sampling distribution of X bar, that means I take one sample mean. Let me show it here. Okay, I have a population of people. This is their, let's say, not pounds, but centimeters. Population mean for height of people, okay, is 1.70 centimeters, okay? I take a sample, which is 64 people, and I found the mean height of people 173. I took another sample, which is 185. I take another sample, which is 164. Is this possible to have different samples with different average heights? Yes, it is possible, right? There might be different people whom I choose. Some of them are shorter, some of them are lower. If I plot these numbers here as an histogram, the distribution of the sample means will have a normal distribution, okay? And the mean of this sample distribution of all X hats, X bar is the sample mean, okay? This is sample mean, X bar is gonna have the population mean, okay? So the mean of the means will have the population mean, okay? How about the standard deviation, okay? How about the standard deviation? It will change with respect to our sample size, okay? Sample size. For example, this is my population, okay? It is 170 and my population is, let's say, 30. And I will have let's say 100 people, okay, as my sample size, 100 people. Then my standard error of the mean, we call it, standard error of the mean will be 30 divided by 100, okay? I will not get the answers after some point, so I don't care whether you send something afterwards, joining the class in the middle and sending something and leaving. It's not ethical, guys, okay? Please be ethical. Don't send. I started discussing about the answer. Now people are sending their results. I'm not gonna be grading them, okay? So the sample, the standard error of the mean, it's called standard error of the mean, okay? So it is SEX bar. So it will be 30 over 100, the square root of 100, and it's going to be 3. So if I have 100 people, my standard deviation or standard error of the mean will be 3 here, right? If I have, let's say, 900 people, the square root is 30, so my standard error of the mean will be 1. So it will be a very very sharp distribution, right? The sample mean distribution will be very sharp, and it will be very good to estimate the actual population mean. Okay, this is the population mean here. This is my population mean, which is 170. Okay, this is known. Okay, and normally it's not known. We pretend that it's not known, and we are trying to find out from the samples. Okay, so if you see that the distribution will be the mean of the means is equal to or very close to the population mean. Okay, that's what central limit theorem says. And then also my standard error of the mean, that means this is SEX. So this is going to be kind of the variance of the means. Okay, variance of the means is going to be the variance of the population or the standard deviation of population divided by your sample size square root. Okay, that's why if I increase from 10 to 1000, like if I say if it is 1000, the distribution was like 50, and this was very small, right? When it was 10 people only in my sample, it will be 50 still, but the standard deviation or sample mean will be standard error of the means will be higher. Okay, this is sharper. Why? Because n is 1000 here. This is much wider. The n is 10, and here the distribution is much wider. Okay, did you understand that that part, guys? Was I clear on that? So this is a nice figure. I have a population of people. I take samples. If I take many samples, and from the samples, if I find out the means, and if I plot them as a histogram, I will have a normal distribution. Whether this population has normal distribution or exponential distribution or uniform distribution, it doesn't matter, okay? It doesn't matter what kind of a distribution I have, but the sampling distribution is always normally distributed. Okay, this is the sample mean distribution, normally distributed. Sample means are normally distributed. And according to the sample size, the variance in my sample mean distribution will change according to this formulation, sigma over root n. Okay, if n increases, the sharpness of my estimation becomes higher. If n is low, it is going to be a wider distribution. Okay. So here is my another explanation. Means based on large samples will have a normal sampling distribution with an expectation equal to the population of the mean, with a standard deviation equal to the standard deviation of the population divided by the square root of the sample size n. Okay, this is going to be the standard deviation of the sample mean. Okay, so this is standard error of the mean, we call it. Now my distribution for the sample means is going to be normally distributed. Mu is going to be the population mean. Okay, and now it's going to be this standard error of the mean, sigma over root n. Okay, so this is what it means, and I should say that 68% of the time the mean is going to be between like mean minus standard error of the mean and mean plus standard error of the mean. This is something that we use many times in against statistics. So if you have data and the majority of the data is going to be between mean minus standard deviation and mean plus standard deviation. Okay, you can see that in normal distribution things. Okay, let's go and check this illustrative example. Now in 1970s, between 20 and 29 years old, men in US had a mean body weight of 170 pounds. We can change, this is height, okay? This is height. And not pounds, but centimeters, okay? Standard deviation was 40 pounds. We can change it to, again, centimeters. We test whether mean body weight in the population now differs. Okay, we are going to do such tests in the coming part of the course. So I have a mean which is 170 of the population, and I'm gonna, this is my population. I'm gonna choose one sample now, okay, and this sample's mean and standard error of the mean we're going to calculate, and then find out if now our mean, our body weight or height of people have changed, right? So through generations, did the body weight or the height change through time as time passes? Okay. So how do I do it, guys? Mu 0 is 170. This is my population mean. And this is my population standard deviation. I know these values from my previous knowledge, from my statistics, okay, that I obtained before. And I will take 64 people each time when I take samples. And I find out my standard error of the mean is 40 divided by root 64, which is 8, right? 40 over 8 is going to be 5. So my standard error of the mean is going to be 5. Okay? Now, for example, I took a sample like this one, and I found out 173 is the mean height of that sample. I took another sample, I found the mean height of that 64 people being 185 centimeters, okay? So I will now work on these two values. Now I'm going to find out, again, do the same thing, x minus mu divided by sigma, right? I'm going to do the same thing here. Now I'm going to have the mean from the sample. This is the sample, okay? I have this group, and I choose one over 64 people, and then found out 173 centimeters as my first sample mean, okay? I took another group, 64 people, and I found the mean being 185 centimeters. Now I'm going to say this is 173 minus 170 divided by 5. This is something that I found before. It is 0.60. If we found the sample being 185, then it will be 185 minus 170 divided by 5, which is going to be 3. Okay, what am I going to do with these information? I'm going to come and say, okay, now this is my z value. This was my distribution, okay? And the distribution was 170. Now I found 183 being 0.6, and the probability of obtaining z being greater than 0.6 is going to be 0.7443, right? From where? From the z table. I change everything from normal distribution to z distribution. And why? Because I want to use the z table, and I can find out that the probability of the area under this curve is going to be 0.27. Okay, and then here, if I go to 185, the z value will be 3, which is far away from 0. So the probability is 0.0010. Okay, so what does it mean, guys? If I find a sample whose mean is 173, it shows that it is not significantly different from 170s. That was my question. Is the height of people in Ankara, in Turkey, in Kayseri, change through time? It was 170 when it was like in 1970s. Now I found 173 in my sample. From that sample, I can say that we will do those kind of tests. We will call them hypothesis tests. We will see them in a couple of weeks time. And if the probability is above 0.05, we will tell this this is above 0.05. Then it means the height of people did not change significantly. But here, if I found a sample mean sample being 185 centimeters, that means the p-value is less than 0.05. This p-value, we will call this p-value a lot. Okay, this is the probability. Okay, this is the probability. So we will use these kind of things very often. Okay. So what did I tell you guys? I have a population, and I can take samples, and I can infer about these samples. Okay, I will tell, okay, my sample mean is 183, and I know from the future, from the history that it was 170. So can I say something about whether it changed too much, it changed significantly or not, the height? We can infer about this finding. Okay. For example, guys, we do such analysis in our research. For example, I have a group of people. Okay. Let's say I have people, let's say 100 people. Okay. And they are cancer patients, lung cancer patients. And I take their images, let's say MRI, CT, or PET images. Okay, let's say we have PET images from them. Okay, it's like an MRI image, let's say, or CT image. And then from that, I will obtain features. Okay, it's called feature extraction. From the images, I will get numbers. Okay, I will get 10.5, 9.7. This is from the first patient. This is from the second patient. 8.5, third patient. Okay, I will have 100 such numbers, and then it is known that, let's say, this number is 5 for healthy people. Okay, and then I'm gonna work on these 100 numbers and compare it with these healthy people's values, and then say, okay, this group of people, this cancer, lung cancer, has this feature, okay, which is above the healthy people's values. So I can say that this is something that I can use for determining the cancer patients in my population. Okay. From that, we can conclude something about the cancer also. Okay, so this was like central limit theorem, guys. Okay, let me once again talk about this. Central limit theorem will tell me something about the population mean. If I do many times the sampling and finding the means, and the sample standard error of the mean will be changing with respect to root n. Okay, we will use this very soon. Okay, now I want to go into a different topic, which is called Z interval and T interval, and I'm trying to introduce a new topic called confidence.
Hojam, before you go, I just have a question.
Sure, please go ahead.
Hojam, in the last illustrative example, you chose 64 as your sample.
Yes.
So the mean would have changed depending on the n you choose, right?
Yes, exactly.
So
This
Which
is
means
for
that
this kind of specific example. I chose
okay.
64 people. I found 183. If this was not 64 by 32, my sample mean would be different, right? And then I would find out a value, and I would do conclusions, or I would do some inferences about the thing that I found. That's the main idea. You found something, 173. Is it some significant, does it show a significant change with respect to the height of people in this age range between 50 years? Like in 1970, it was 170. Now it is 2020. What is it? I found from my sample 173. So is it significant change or not? That's what I'm trying to do. Okay, I have something from normal people. I have a number from let's say diseased people, and I'm going to compare them. This is, let's say, I will have a normal data and I will have disease data, diseased people data, and compare them whether they are significantly different from each other. That's why we use these z-statistic and so on. Okay, comparisons with a known value or unknown value. We will do those kind of things. Emmanuel, was my answer clear, or?
Thank you, Jamus. Clear.
Okay, if my sample size changes, this z value will change, and the probability will change. The z value will change, and the probability, the p value will change. Okay, we will call this p value, probability, and it will change our conclusions. Conclusions about what we found from my experiment, from my sampling. Okay, the whole idea is I am sampling 100 cancer patients. There are millions of cancer patients, but I can only do some research on 100 cancer patients, and I'm trying to find out something that can be used to detect a disease. Okay, that can be a nice parameter that I can use to differentiate between normal people and cancer patients. Okay, so that's why we do these kind of statistical results, statistical analysis. Okay, so it will be again something very important. We will use this confidence interval. You're gonna see these kind of things in many engineering papers, engineering talks. You're gonna hear this confidence interval. What does it mean? We're gonna mainly focus on the mean, okay, population mean. We are trying to find out, estimate the population mean. We are trying to find out or estimate the population mean, okay? For example, the population mean is 170. I don't know this, but I found from my sample 173. Is this a good number? Because they are close to each other. If I found 160, is this a good number? Again, significant difference. I should be able to talk about this confidence interval in order to say that, yeah, that's a good, I will tell that 95%, I am 95% confident that the mean is in this interval. Okay, I'm not going to estimate only one number, but using this 173, I will say the mean of the population is in this interval. And I am confident 95% of the time that's the case. Okay, so this is something that we will cover now. Let's do that one by one. Okay, I have a sample mean, and I'm trying to estimate the population mean. And how can I be confident that X hat, the sample mean, is close to mu? I found 173. Is it close enough? How can I be confident about that? I found a sample proportion. Okay, we always talked about means, but we can also say proportion or percentage. Okay, how can I be, this is my sample proportion. P hat is sample proportion. Okay, I found from the AGU students, like I asked 100 students, do they have any bikes or not? And I found that 20% of the students that I took sample from have a bike. So is this something close to what the actual number of people who have bikes in the AGU campus or not? Okay, that's an example of sample proportion. So we will be talking about how close the sample statistic, like this proportion, sample proportion, and sample mean, you see, hat and bar, these are called sample statistic. Okay, sample statistic. It's not population parameter. They are called sample statistic. Okay, so how can I find an interval in which we can say I am this confident that the actual unknown parameter is going to be in this interval. Okay, confidence interval. It's in Turkish we call it güven aralığı. Okay, güven aralığı. So rather than using just a point estimate, like X hat is a point estimate, P hat is a point estimate, okay, point estimate. That means it is one number from a sample. From that sample, how can I say the mean, the real population mean is in this interval, okay? This is something that I found, X hat. But what is, like the mu is, I will say the mu is going to be in this interval. This is X hat, and this is the lower bound, this is the upper bound, okay? My mu, the population mean is going to be in this interval, L, between L and U, lower boundary and upper boundary, okay? So lower values and upper values. We're going to find out these lower and upper values, and we will call them the confidence interval, okay? So I am trying to find out my population mean. I found a number, 173. Is it close enough? I cannot say it is a good estimate. I will use a confidence interval concept in order to say, okay, I am 95% confident. I am 99% confident that the mean of the population is in this interval. Okay, this is how we will be interpreting this confidence interval concept. Okay, so this is what I mentioned. We will be mainly using 90% confidence, 95% confidence, or 99% confidence. And this 95, if I have 95% confidence, then this alpha will be 0.05. Okay, this is something that I said P less than 0.05, right? We will use that very many times. So alpha is something that we will be referring to. It will be confidence coefficient. Okay, confidence coefficient is 1 minus alpha is something that we will choose. I will choose alpha will be 0.05. What does it mean? My confidence interval will be 95%. Okay, what does it mean? If I choose if this is my let's say confidence interval, and this is X bar, and in 95% of the time the real population mean will be in this interval. Okay, let me write this. It comes later, maybe I will do it next time. The greater the confidence interval, the more confident we can be that confidence interval contains the actual population parameter. Okay, so let's see. Here is my standard normal curve. I will have zero mean. This is my mean. Okay, I will have different z values, which we did very like in the previous hour. And this is z alpha over 2. Alpha was our choice. Okay, for example, if alpha is 0.05, this will be 0.025. This will be 0.025. Okay, this is symmetric. Okay, 0.025. That means 95 times of the 95. The area here is 95% of the whole thing, right? The whole probability distribution, 95% of this thing is in this area between minus z alpha over 2 and plus z alpha over 2. And only for the lesser part, 0.05, 0.25% of the time, the value is less than this value, and 0.05, 0.025% of the time, this value will be greater than, okay, z will be greater than z alpha over 2, will be 0.025, okay? The probability of obtaining a z value which is greater than z alpha over 2, which is z 0.025, okay, is going to be like only 0.0025 probability will be that. Okay, so this is something. For example, let's continue with some examples. Okay, so here is my confidence interval. We will use this very often. Okay, let me write it like that. I will find a sample mean, and I will say my confidence interval will be x hat, x bar, plus and minus my z alpha over 2, which is something that I will choose, or the question will tell you. Okay, question will tell you that. And then you will be multiplying this with sigma. Again, this is the population variance or standard deviation. Again, this is given. Okay, this is given. And then divide by square root of n. This is the sample size of your sample. Okay, 64 people in order to find out this value. Okay, so for example, we found 163 as my sample mean. I'm going to say plus and minus z alpha over 2. We will say this very soon. And sigma was, let's say, 40 divided by 64. Okay, and then finally I will have 173 plus and minus z alpha over 2 divided by times by 5. Okay, so my confidence interval will be 173 minus z alpha over 2 times 5 up to z, like 173 plus z alpha over 2 times 5. Okay, this is gonna be my confidence interval. What does it mean? It's gonna be 95% of the time the mu will be in this interval. The population mean will be in this interval. Okay, before we go, let me do one example, and I hope you're gonna understand what's going on. Okay, so are you with me, guys? Yes, one moment please, just 5 minutes, and then I will be done. Okay, I have 126 police officers, and they are constantly inhaling automobile exhaust fumes in Taksim area. Okay, there are police officers in that area, and they are constantly like inhaling, soluk almak, okay, inhaling automobile exhaust fumes, and they have an average blood level, lead level kurşun kanlarındaki kurşun seviyesi, blood lead level concentration is 29.2 micrograms per deciliter. Okay, so my X bar, this is from this 160 people, 126 people, police officers, and I found 29.2 being my sample mean. This is sample size, okay? Sample size, sample mean. So what is known from previous experience, and the blood level, lead level of the random selected police is normally distributed with a standard deviation of 7.5, okay? So we found that like normally it's like 7.9 is going to be the standard deviation. It is known that the average blood lead level concentration of humans with no exposure to automobile exhaust, if they don't inhale automobile exhaust, no lead levels in their blood, and it's going to be 18.2, okay? So the mu is 18.2, okay? It is known that normal people without automobile exhaust too much, the mean level is 18.2. Here's the question: is there convincing evidence that the policemen exposed to constant auto exhaust have elevated blood lead level concentrations? Normally, normal people, it is 18.2. And I found from the police officers in Taksim, 126 police officers, and I found 29.2. Okay? Exhaust inhaling. Is this significantly different from this one? How can I say that this is significantly different? Anlamlı bir fark var mı? Egzoz soluyan biri normal insana göre kanındaki kurşun miktarı anlamlı bir şekilde değişmiş mi? That's the question. Okay? Did the blood lead level change when they inhale exhaust fumes in Taksim? Okay, I have 126 people, like a sample size, and I found that 29.2 is the lead level that I'm measuring from their blood. Is this something important? Is this something significant? How can I do this significance test, if this is significant or not? Here is what I do. Okay, I'm going to give you in the questions 95% confidence. What does it mean? If I have 95% confidence, then alpha is 0.05. So 95% of the time, I will have my values in this range. Okay, alpha is 0.025. So from this, you can see 0.025 is 0.2, and sorry, I'm gonna come here, 0.025, somewhere between these things. Okay, let me be more specific. I need to find out something here, like this is the probability, 0.025. This is the probability. Where does it come from? 1.96. So the z value, which will correspond to the area being 0.025, is 1.96. So if I tell you my alpha is 0.05, or I'm using 95% confidence, what's the z value that you're going to use in this confidence interval formulation? Do you remember the formulation? X bar minus z alpha over 2 times sigma over root n, and this is going to be my lower bound, and the upper bound will be x bar plus z alpha over 2 times sigma over root n. Okay, this is my lower bound and this is my upper bound. What is the basic idea? The population mean will be in this interval for 95% of the time. If I do this 100 times, 95 times of the 95 times, I'm gonna get my population mean in this interval. Okay, so Melissa says something. Let me check that. That is 95% confident that the mean blood level concentration of all policemen exposed to constant auto exhaust is between 27.9 to 30.5, right? We're going to do this calculation here. Okay, so this is 29.2, this is 1.96, this is given as 7.5, this is given as 126. If I do the calculations, I'm going to find out this is the lower bound, this is the upper bound. Okay, what does it mean? The people who are exposed to exhaust fumes will have a mean value, okay, mean value in this interval. Okay, my confidence interval will be this, between almost 78 to 30. If I had a sample like 29.2, if I make the sampling many times, I can see that 95% of the time, this mu, who has policeman, who has constant auto exhaust, the blood lead levels, kanındaki kurşun miktarı will be in this range. Okay, so what was the healthy people's range? 18.2, right? That was in the question, 18.2. So I'm going to come back and say, is this 18.2 in this range? No, it is not. So I can say that. There is no convincing evidence that the policemen exposed to constant auto exhaust have. There is convincing evidence. Yani bizi ikna edecek bir delilimiz var mı? Yes, we have. The statistical study that I have done tells me that the mean blood level concentration of all policemen exposed to constant auto exhaust is between this two values. Okay, it will be between 37.9 and 27.9 and 30.5, and in normal people it is 18.2. So it is I have an convincing evidence that the policemen who are exposed to constant auto exhaust have elevated blood lead level concentrations. Okay, I can do this for cancer patients. I can do this for different type of things. Okay, so 95% confident means that you would expect 95% or 950 of the 1,000 intervals to be correct. That is to contain the actual unknown value. Okay, arkadaşlar, how do I calculate confidence interval? What do I need to calculate the confidence interval? Please write to chat, and this is going to be the last thing for you. What do you need to calculate a confidence interval for your question? Okay. What do you need to calculate the confidence interval? Let me record this. I don't know the population mean. That's what I'm trying to estimate. But I know the population variance, okay? Population variance or standard deviation. This is known. Okay? For this is called Z interval, okay? Z interval. Population standard deviation is known. It is called Z interval. What was the population? What was the confidence interval? X hat minus Z, my confidence interval, times sigma over root n. So what do I need? Plus and minus. What do I need? I need the sample mean. I need my confidence interval. So I will calculate my Z value, 196 or something like that. I need the population mean. Okay, this is given a population standard deviation. I need the sample size. If I know these, I can find out the confidence interval being lower bound and upper bound. And what does it mean? The population mean is going to be in this interval 95 times of the day. 95 times out of 100 times. Okay, that's why I cannot say, okay, I found one sample mean and this is my confidence interval. Maybe it is not where your mean is, right? So you may say maybe 5 times out of 100 times your confidence interval may not include the actual population mean, but you're going to say I'm 95% confident that my mean population mean is going to be in this interval. Okay, so please try to review this topic. We will have kind of quiz, again very important quiz after the break. Okay, we will have the 19 Mayıs break. After that, we will meet again, inshallah. In 2 weeks' time, we will meet again, and in 2 weeks' time, I'm going to upload some videos. I'm going to upload some questions for you, and I want you to get ready for those. And we will have a quiz once we are back. Okay, inshallah. That's all for